Hello friends, in this video we're going to talk about molecular orbital theory as applied to polyatomic molecules, and by that I mean molecules which have 3 or more atoms. So we're going to start with the simple molecule water, which of course only has 3 atoms, and look at how molecular orbital theory applies to that and introduce the concept of basis sets to construct molecular orbitals. And then we'll look at a slightly larger molecule, formaldehyde, which of course has 4 atoms. We'll also study its basis set of atomic orbitals that form its molecular orbitals. And finally, we'll introduce Huckel molecular orbital theory and how that applies to pi electron systems. So water. We know that water has 1 oxygen and 2 hydrogens. And what we call the minimum basis set is the minimum number of orbitals that are necessary to describe the bonding in a given molecule. So we're going to use the valence shell of the molecule to construct those orbitals. And in this case, that means that for water we have a hydrogen atom which has a 1s orbital. That's its valence shell. The other hydrogen atom also has a 1s orbital. And of course, oxygen, its valence shell, has 2s and the 3 2p orbitals, the 2px, the 2py, and the 2pz. That means that we've got 6 atomic orbitals, and the general rule of thumb, of course, is that the number of molecular orbitals we get from our linear combination is equal to the number of atomic orbitals we put into that linear combination. Since we have 6 atomic orbitals in our minimum basis set, then we're going to get 6 molecular orbitals in the computation. Since we have 8 electrons in the valence shell of these atoms, 2 electrons, 1 from each hydrogen, and then for oxygen we have 6 electrons in the valence shell. That'll be a total of 8 electrons that we'll use in the molecular orbitals that we're constructing to form our electron configuration for the molecule. Alright, so here's an example of a linear combination of these 6 atomic orbitals. We have the 1s orbitals on the hydrogens, the 1s orbitals on, the 2s orbital on the oxygen, the 2px orbital, the 2py, and the 2pz. So when we talk about linear combinations of molecular orbitals, as you may recall from our discussions of diatomic molecules, that we take a sum of all of these orbitals, and we multiply them by, at this point, an unknown coefficient. So the purpose of the computations when we do these things, and essentially the crunching that goes on in the computer programs that we're using to generate molecular orbitals, what we're trying to do is figure out what the coefficients are corresponding to these molecular orbitals. So we'll get 6 different sets of coefficients corresponding to each of the 6 molecular orbitals that we get out. Now, one additional thing to consider is that the coordinate system and how we define that, the z-axis in these molecules is always defined as the main symmetry axis of the molecule. And in the case of water, that z-axis would be the axis that goes through the oxygen atoms, the oxygen atom, and then rotation by 180 degrees about that axis would actually yield the same molecule from the same perspective. In this case, we're going to define the y-axis as corresponding to the plane containing our planar molecule. So the H2O molecule would be corresponding to the YZ plane, and the x-axis would be perpendicular to that plane. The definitions of the y and the x-axes will differ from textbook to textbook, but the z-axis is always considered to be the main principal axis of the molecule. So we do our calculation and we get our 6 molecular orbitals out. This diagram shows the molecular orbitals that we get out of it as we look at it. So here are our 6 molecular orbitals that correspond to the results of our computation. And if we just begin to look at these orbitals, and we can figure out what atomic orbitals are used generally in their construction. So looking at the lowest energy orbital here, we can quickly surmise from this particular illustration that the lowest orbital is largely a 2s orbital on the oxygen and the 1s orbitals on the hydrogen atoms. They will overlap constructively, form delocalized picture of the electron in that particular molecular orbital, and on the next slide we'll be able to see this more clearly. Next, going on to the next higher energy orbital, we can see that we have a 2p orbital on the oxygen, and it falls along the y-axis as we defined in the previous slide. So this orbital consists largely of a 2py orbital overlapping with the 2p with the 1s orbitals on the hydrogens. Now, one thing you'll note here as we go back to this is that there is a situation where we kind of right down the middle of the molecule, we're going to get a destructive overlap. So we'll notice that on this side of the molecule, the signs of the wave functions are the same, so we will get constructive interference there. On the other side of the molecule, we'll get constructive interference because the signs are the same, and we'll get a nodal plane right down the center of the molecule. You notice that we get the nodal plane in this orbital, but in the lower energy orbital there are no nodal planes, so we get delocalization over the entire structure of the molecule. So going on to the next orbital, all right, what we'll note is that this orbital here is actually a 2pz orbital on the oxygen, overlapping in a constructive way with the 1s orbitals on the hydrogens. Then moving up to the next orbital, we have the 2px, all right, which you notice is perpendicular to the plane of the molecule, and that has no involvement whatsoever. You notice there's nothing here for the hydrogens. So the hydrogen 1s orbitals do not overlap with this particular orbital at all. So this molecular orbital is essentially just a 2px orbital on the oxygen atom. Now, we have 8 electrons, as you recall, in our valence shell, so we have constructed enough orbitals right now to go ahead and fill in these 8 electrons. Again, the Pauli exclusion principle says 2 electrons per orbital, so here are 8 electrons, so this corresponds to the ground state electron configuration for the water molecule. Now, of course, we have 6 orbitals total, only 4 of them are filled in the ground state. So we go up to higher energy orbitals. We see here that we've got a 2pz orbital, and that the 1s orbitals on the hydrogens are such that they have an opposite sign to this 2pz bottom lobe. So there is a node corresponding to the destructive interference that occurs in that region. This is called an antibonding orbital because the antibonding orbitals have higher energy than the atomic orbitals. So here it would be the energy of the 1s orbitals on the hydrogens, and here the energy of the 2p orbitals on the oxygens. This molecular orbital up here that's antibonding has higher energy than the atomic orbitals. That's why it's called an antibonding, because it's more stable for the electrons to remain in the isolated atoms than to go into this antibonding orbital. And then the orbital we have at the very top of our illustration here has a 2py orbital. Of course, that 2py orbital is directed along the y-axis. And we'll also note that the overlap, because of the opposite mathematical sign between the 1s orbitals and the 2p, corresponding 2p lobe, we get destructive overlap in that situation. So we have a nodal plane between the oxygen and the hydrogens. And once again, the energy of this one is greater than the atomic orbitals, so this is also an antibonding orbital. Now, so what we'll notice here is that what we have all together are 3 bonding orbitals, And here are our three bonding orbitals that are lower in energy, corresponding to the, the molecular orbitals. And then we actually have what we would call a non-bonding orbital here, because that is just, notice, as we said earlier, that is really just a p orbital on the oxygen atom. So it's not really involved in bonding at all. So we just refer to that as a non-bonding orbital. And of course you'll notice that in the ground state we have 2 electrons in that non-bonding orbital. So here's another diagram which shows these molecular orbitals in water, but actually shows the illustration of the orbitals as they might look when we look at the overlap. So we'll notice that the lowest energy orbital, which is completely constructive, has delocalization over the entire molecule. So electrons which are in this particular low energy orbital are delocalized over the entire molecule. Those 2 electrons are delocalized. If we move up in orbitals, again, we'll notice that we've got constructive interference on this side of the molecule, and on this side of the molecule, as mentioned before, there is a nodal plane down the middle of the molecule, but this is a bonding orbital because it's lower in energy than the atomic orbitals. We'll also notice that as we move up, we also have constructive interference here with electrons delocalized over that region, and that's also a bonding orbital. But if we go up to the next one, all right, which is just a 2px orbital, as we mentioned before, that's just non-bonding. And then we have the 2 upper energy orbitals, which clearly show anti-bonding structure because of nodal planes between the oxygen atom and the hydrogen atoms. And again, their energies destabilize bonding in the molecule. All right, okay, so let's move on to formaldehyde, slightly larger with 4 atoms. And we're going to ask the same question. What's our minimal basis set in this molecule? So we've got 2 hydrogens, each of which will contribute a 1s orbital. We've got a carbon, so its valence shell would be the 2s and the 2px and the 2py and the 2pz, as well as the oxygen, which has the same valence shell. So now we have a total of 10 atomic orbitals, and that means we're going to get 10 molecular orbitals when we do the calculation. And this is something that in class we'll actually use Spartan to do some calculations for this molecule. We will have, again, if we start counting up valence electrons, 1 electron from each hydrogen. Then we've got 4 electrons from the carbon and 6 electrons from the oxygen, so that we have a total of 12 valence electrons in this molecule. All right, so we go through and we construct our molecular orbitals, and we get something that looks like this. Now, this particular illustration may be confusing, and that's why we're going to go back and do a calculation in class. But this shows the molecular orbitals that are generated with low energy at the top and high energy down at the bottom. And so these 2 orbitals up here will correspond to the lowest energy orbital, and I'll come back and talk about those in a couple of minutes. And then we've got increasing energy as we go down to these orbitals here, and then back up so that this orbital here, the next orbital above it in energy would be this orbital. So in terms of energy, we're going in this direction. And then increasing energy as we go down. So the orbitals that are shown here in this illustration, this is the highest energy orbital right here. So I hope that's clear. Again, we'll be talking a little bit more about this in class to help you understand. And then this illustration here at the bottom, which has the different pretty colors, very colorful illustration, is actually something that's known as the electrostatic potential surface, and basically this shows how charge is mapped out over the electron density of the molecule, where the red corresponds to excess negative charge, and that the blue corresponds to excess positive charge. And we have the situation, which is perhaps not surprising because we have an oxygen here, and we know oxygen being electronegative is going to draw electrons toward it. So we have a molecule with a dipole moment with the negative end up here toward the oxygen and the positive end down here in this region where the hydrogens are. Now, if you count the number of orbitals here, you'll clearly see that we don't have 10 molecular orbitals, which on the previous slide we talked about our minimal basis set creating 10 molecular orbitals. The other thing that we'll make note of here is that these two orbitals at the top correspond to inner shell orbitals, and that if we look at them closely, we'll see that this orbital here is essentially a 1s electron, a 1s orbital on the oxygen, and this orbital here is essentially a 1s orbital on the carbon. These inner shell orbitals show very little overlap with orbitals on other atoms because, in general, the much lower energy inner shell orbitals do not form molecular orbitals by overlapping with orbitals on other atoms. They're not very much involved in the bonding at all, which of course you know from your basic chemistry classes. It's generally the valence shell that we're interested in when we talk about the chemistry of the molecule. So of the orbitals here that correspond to overlap of valence electrons, we're talking about the ones that here and here corresponding to valence electrons, and we see that we have 6 of those. These are the orbitals that are going to be occupied. Remember on the previous slide we said there were 12 valence electrons in this molecule, and what that means is that we've got 1, 2, 3, 4, 5, 6, so 2 electrons here, 2 electrons here, 2 electrons here, 2, 2, and 2. So this is our HOMO, the highest occupied molecular orbital that we'd have with our 12 electron valence shell. I hope that's clear. So let me again just reiterate. We've got 2 electrons here, 2 electrons here, 2 electrons in this one, 2 electrons here, 2 electrons here, 2 electrons here for our total of 12 electrons in our ground state for the formaldehyde molecular orbital configuration. And again, what we'll do is we'll take a closer look at these molecular orbitals after we've done some computations in the Spartan program. And we'll take a closer look at things like the electrostatic potential map to help us understand electron distribution within the molecule, and this will also help us understand the reactivity in some molecules. So Huckel molecular orbital theory promised at the beginning of this video that we'd be talking about that, but I think we've actually reached the point where we just need to digest what we have just learned about molecular orbitals in polyatomics, in water and formaldehyde, and then after a little bit of thinking we'll come back and talk about Huckel molecular orbital theory in our next video. So stay tuned.